I'm Frank Höfler and I'm with Thermo Fisher Scientific, and I'm talking about ion chromatography with mass spectrometry. Let's talk about the benefits of ion chromatography with mass spectrometry first. Liquid chromatography, HPLC, with mass spectrometric detection is widely used so far for environmental analysis, food and beverage analysis, as well as in the pharmaceutical analysis scheme. Ion chromatography has the benefits that it gives a high selectivity and specificity for small ionic compounds, which typically elute in the void volume of a reversed phase HPLC column. We also see an advantage when we are looking at mass spectrometric detection in comparison to the conventional conductivity detection, which is used with ion chromatography. The advantages here are a higher mass selectivity, specificity, which is very important for complex matrices, and also a higher sensitivity specifically for small organic ions. One of the things which is key for the interfacing of ion chromatography with mass spectrometry is a device which is called a suppressor. The suppressor converts the mobile phase used in ion chromatography, which is either a strong acid or a strong base, into a pure water, which is 100% compatible with the MS system. So this is really a key part here and avoids that we are getting ion suppression, a common problem in LC-MS, that we are not corroding any parts of the MS by pumping in a pure acid. Converting that into pure water really made ion chromatography MS a viable technique. Why are we using mass spectrometric detection? One of the major reasons is analyte confirmation. We want to really ensure that the analyte which is eluting from the ion chromatographic column is the analyte we are suspecting. And conductivity detection is a very universal technique which detects all ionic compounds. The MS here gives us additional information like the mass to charge ratio of the certain peak, which then helps us to identify and confirm that peak. Let's move on to the next slide and talk a little bit about the mass spec we are using here. In this case, and in all the examples I'm presenting today, we are looking at a low-cost single quadrupole mass spectrometer, which is more designed as a detector for chromatography. And it is widely used also with IC to analyze specific compounds, which typically are at low concentrations. So what are the key components we are looking here at? I mentioned the suppressor, which acts as a desalter and really makes the technique possible. In addition to this, we are most commonly using anion generation. Anion generation is a technique which allows us to perform gradients with an isocratic pump and also purify the anions using a trap column inline, which then results into lower background within the mass spec after suppression. So the MSQ Plus mass spectrometer is designed to fulfill the needs of IC. It has a very good sensitivity for small ions like fluoride, chloride, nitrate, nitrate, and so forth. And I will show you some examples later on. It allows us to operate the mass spec as a universal detector in the scan mode to record mass spectra and help to confirm peaks or even to identify unknowns. In addition to this, we can also operate it in the single ion monitoring mode to be very sensitive and very selective. And that allows us to record multiple channels at the same time, which are then specific for one mass to charge ratio or just for one analyte ion. It has an outstanding performance, results in very low noise. And since most of the ions analyzed in ion chromatography are anionic, we operate the MS in the negative mode. In the negative mode, we also see less background noise and really have a very good sensitivity. The whole system, the IC as well as the MS, are controlled by a Chromeleon data system, and we can utilize that in combination with conductivity or other detectors to really generate holistic reports and validate our examples and results. Moving on to the next slide, I'm giving you an overview of a typical flow diagram. As presented before, we are using a mobile phase, and in the case of anion generation, we are using just pure water. The pure water then is pumped by a 100% metal-free polymeric pump into the anion generator cartridge. where we then generate our eluent electrolytically on a mouse click. The advantage here is doing that on the high pressure side, that we can generate high purity hydroxide eluents without having the risk of contaminating the eluent with carbon dioxide, which is in the air. Afterwards, we are using a continuously regenerated trap column which purifies the eluent before it goes into the injection valve where we are injecting our sample. We can either use manual injection using a syringe or an autosampler for high sample loads. After the injector, we pump the samples with the eluent through our separator column and separating the ions accordingly to their charge and to their molecular mass. So the small singly charged ions are typically eluting first, and the multiply charged larger ions are typically eluting last. After the separation, we pass our effluent through a suppressor and convert our eluent into pure water while we convert our analytes into the corresponding acids. Those are then going through a piece of tubing and a T-piece, and we often also add in a flow of an organic solvent, which is then used to enhance the electroionization process, the ESI process, which is a part of transferring our ions from the liquid phase into the gas phase and bringing them into the vacuum system of the mass spec. Since the conductivity detector is a non-destructive detector, we can use conductivity detection first and mass spectrometric detection afterwards, which allows us here to generate more information out of a single run. Then, in addition to that, we are using our Chameleon data system all on one computer to control both the ion chromatography system as well as the mass spec, and using the software also for data handling, reporting, and so forth. Moving on to the next slide, I'm showing a typical example of the separation of common anions, starting with fluoride as the smallest ion first, which is recorded in the single ion monitoring mode at mass to charge ratio of 19. In addition to that, you see clearly that there is closely eluting to fluoride formate, but the mass spec puts them into different channels because they have detected at different mass to charge ratios. And if you also have acetate in there, also another organic ion which is eluting closely to those, we see no problem here either, all separated into different channels because they all have different mass to charge ratios. This makes it really easy to increase the certainty about which analyte is eluting from our IC column, and specifically if we have large concentration differences, and I will show you examples later on, it makes it a very viable technique. We see further ions here eluting like nitrite, nitrate, bromide, sulfate, which is detected here as a singly charged ion because after the suppressor we have a neutral pH value, and then sulfate is detected as a singly charged ion at mass to charge ratio of 97. We also see a small isotope peak at mass 99, which comes from the sulfur 34 isotope here in sulfate. And we can use that information again to really identify that the peak we are detecting is sulfate and nothing else. What else could it be? What else is detected at mass to charge ratio 97? Phosphate. And again, phosphate is typically a triply charged ion, but at the neutral pH value it also elutes here as a singly charged ion detected at mass to charge ratio 97. And here we really take the advantage of the ion chromatographic separation because we are separating both ions in time and have no problems with any misidentification or misquantification. Citrate is in this example the last eluting ion with a retention time of about 14 minutes. Let's move a little further on and take a deeper dive into some other ion analysis. We talked about that anion analysis is very common, but we can of course also do cation analysis. And one of the areas where ICMS is mainly used are small amines. And those are typically difficult to detect because they do not have a very high response factor in conductivity detection. They have a small mass, and they are ideal for MS detection as shown here in this example. We also see that these ions are closely eluting, and the MS really helps us here to separate all these peaks make the peak identification of the peak start and the peak end very easy and straightforward and get good quantitative results. Going forward, of course, low-level analysis is typically a problem, specifically in the presence of a major abounding ion. In this example here of the determination of low-level potassium in the presence of diethanolamine, we really see the power of ICMS. On the conductivity trace, which is shown here in green, we see that potassium is eluting as a tailing small peak on the tail of the diethanolamine. If we are using the mass spec and really looking at the mass to charge ratio 39, which is selective for potassium, we have no problems because we do not detect diethanolamine at all, and we can nicely detect the peak start, peak end. We have no tail, no co-eluting peak is visible, and we get a very high sensitivity as well in this example. Let's move on to the next example, which is a very interesting one, because in this example we are showing the separation of anionic, cationic compounds in one run. And what are the species we are looking here? Those are arsenic species. Arsenic typically is determined as a total content with ICP-MS, very sensitive and selective, or with cold vapor atomic absorption spectrometry. But not all arsenic species are highly toxic. Some are, some aren't. So really finding out and analyzing what species are in the sample in addition to the total content gives additional value. And since arsenic can be anionic or cationic, we need to separate both of them and would like to detect them typically in one run. What have we used in this example? We have utilized a dual channel IC system, equipped one channel with an anion separator column and the second channel with a cation separator column, a mixed mode column in this case. And we have worked out the method that first the anionic species are eluting, being detected with a mass spec, and afterwards the cationic species. So the total runtime for this example is about 30 minutes, and we are able to analyze all inorganic as well as organic arsenic species here. Let's move on to some other examples, real-world examples. Oxyhalides and bromide in drinking water is another area where ICMS is used. Those compounds are disinfection byproducts, typically being generated by the ozonization of drinking water. And if the drinking water contains bromide or iodide, we have the risk that we oxidize them and form iodate, bromate, or chloride here as well. Those compounds are cancerogenic, toxic, and need to be monitored at very low levels. And again, in this case, as demonstrated here, we can selectively and very sensitively detect these oxyhalides in the presence also of other inorganic ions, which can be 100 or 1,000 times higher in concentration. The mass spec with the mass selective detection allows us to only focus on the target analytes and here really selectively detect those at very low concentrations. Let's move on to the next example. Another example in the area of disinfection byproducts, which created a lot of interest over the last years, are haloacetic acids. Haloacetic acids can also be formed during the disinfection process, and those can be very cancerogenic and have to be determined at very low levels. The problem with haloacetic acid is that they are thermally labile. In the past, most commonly GC was used, GCMS or GC with electron capture detection, but that required manual derivatization of the analytes. So if someone wants to analyze the haloacetic acids direct, because the derivatization can be error-prone, is a relatively difficult technique which needs skilled operators, then IC with mass spec detection is the right technology here. Here we see a nice separation of 9 haloacetic acid, starting from the monochloroacetic acid up to dibromoacetic acids and so forth. And specifically, the brominated acetic acids are the ones which are thermally labile, and we perform the separation even on the IC column, typically at 15 degrees Celsius or below, to avoid that we see any thermal degradation of the analytes. Moving on to the next example, and as pointed out before, one of the challenges are typically the high matrix concentration. In this example, we are analyzing low ppm levels of chloroacetic acid and bromoacetic acid in 0.1% sodium chloride solution in a high salt content like seawater. And as we see here in this example, we only detect the chloroacetic and bromoacetic acid. We used the mass spec and looked only at the mass to charge ratios in the area of interest. So we are not detecting chloride here at all. It's invisible in this experimental setup, and really gives us here a very high sensitivity and selectivity. If we would have used conductivity detection, we would have probably only detected chloride for that example. Moving on to the next example, pharmaceutical analysis, and we are showing here an example of biphosphonate analysis and excipients using capillary ion chromatography. Electrospray ionization is a technique which works best at low flow rates. So in all the examples we had shown previously, we used 2 millimeter columns with flow rates of typically 1/4 ml per minute. But going to even lower flow rates helps us to increase the sensitivity of the electrospray ionization process and boosts up the sensitivity in the mass spec. In addition to that, we are also bringing less matrix into the ion source, and maintenance like cleaning of the ion source is less an issue if we reduce the flow rates. So in this example, we are using a capillary column with a flow rate of 10 microliters per minute, and we are adding 20 microliters of acetonitrile to enhance the electrospray ionization process in this example. And we are able to separate different organic acids here, like benzoate, hydroxybenzoate, then citrate, and chlorodenate, and other ions here as well in this example. We can, as we see here again, take advantage of the selective ion monitoring and really put all these analytes into different channels, which makes quantification and analysis very easy and straightforward. So in summary, I would like to conclude that the chromatographic separation using an RFIC system with eluent generation and a continuously regenerated trap column, as well as an electrolytic suppressor, makes ion chromatography with MS detection easy and viable. We are generating very high purity eluents, which result in very low background ion contamination of the MS. We have a very good sensitivity. It is easy to do gradient separations on the mouse click. The pumping system of the IC is only using water, and the suppressor converts all the eluent ions into pure water, so we are eliminating any ion suppression effects on the MS side. Many samples can be directly injected onto the IC system without derivatization and making sample preparation easy and straightforward. A lot of the times we only have to use a simple dilution or filtration step. ICMS can be used to confirm the identity of small polar ions and increase the analytical certainty that we are really identifying the right compounds here. Furthermore, I would like to highlight some resources if you would like to get more information. We have several application notes published so far, which you find on the Thermo Fisher Scientific website. And these application notes give you detailed information about the sample preparation, all the chromatographic and MS condition, and make it easy for you to reproduce our data. In addition to this, I also would like to highlight 2 publications here. One is a poster and one is an article from the American laboratory. That one is of high interest due to the arsenic analysis, and we all learned about arsenic from the Dr. Oz show, where he found higher arsenic contents in apple juice. Thank you very much for your attention, and I hope you enjoyed the presentation.